Hello and welcome to a new video on IGCSE Physics Classified Paper 4. In this video, we shall be discussing pressure. Figure 2.1 shows a measuring cylinder that contains a colored liquid. The measuring cylinder contains 82 centimeters cubed of the liquid. The density of the liquid is 950 kilograms per meter cubed. The height h of the liquid in the measuring cylinder is 0.094. Calculate the pressure due to the liquid at point X. So in order to calculate the pressure, we use the formula pressure equals density times gravity times height, rho GH. And we are given everything we need here. So gravity is 10 or 9.8. Density is 950. And the height is 0.094. Everything is given, so all we have to do is to multiply the three values together, and we get 893 Pascal. In double I, we are told the true pressure at point X is different from the value calculated in BI. Explain why. The idea is that we did not take atmospheric pressure into account, so the true pressure should have been rho GH plus atmospheric pressure. However, in our calculation, we did not include this, so therefore our calculation will be less than the actual value. A rectangular container has a base of dimensions 0.12 times 0.16. The container is filled with a liquid. The mass of the liquid in the container is 4.8 kilograms. Calculate the weight of the liquid. So the weight of the liquid is given by the formula W equals M times G, which is 4.8 multiplied by 10, and that gives us 48 newtons. Then we are required to find the pressure on the base of the container. So we are given the weight, which is a force, so the F equals 48. And we are given dimensions of the base, so we can use them to calculate the area. So the area would be 0.12 times 0.16. So we just use the calculator to figure this out. So 0.12 on the calculator multiplied by 0.16. This shall give us 0.0192. So this would be the area. Finally, the pressure is force over area. So we divide the two numbers by each other. So 48 divided 0.0192. This gives us 2,500 Pascal. So let's check the correct answers. So we do have 48 newtons here and 2,500 Pascal. Finally, in B, again, we are asked to explain why the total pressure is greater than the calculated value. This is because we did not include atmospheric pressure here as well. Figure 1.1 is the top view of a tank in an aquarium. The tank is filled with salt water. The depth of the water is 2. The density is 1.1 times 10 to the power of 3. Calculate the pressure due to the water at a level of 0.8 meters above the base of the tank. So again, here we are given density and depth. So we're going to use P equals rho GH. However, we need to figure out which height to use because we're given two different heights. We're given this height here, and we're given this height here as well. So rho is the density. So this is just written as is, and G is equal to 10. No creativity there. But we need to figure out what the height is going to be. So the idea is that the depth of water is 2, and we want the pressure at a level of 0.8 above the base of the tank. So we have a base of the tank like this. The water is up to 2 meters, but we want the pressure at 0.8 meters. So we want the pressure at this point here. So we need to calculate the depth of the point at which we want the pressure. So this depth here would be simply 2 minus 0.8, which is 1.2. And we plug that as the height in the formula, and we get 13,200, or to two significant figures, 13,000, which is 1.3 times 10 to the power of 4. All the sides of a plastic cube are 8 centimeters long. Figure 3.1 shows the cube. The mass is 0.44. On the moon, the weight of the cube is 0.7. Calculate the gravitational field strength. So the gravitational field strength is given by W equals mass times gravity. So therefore, 0.7 equals 0.44 times gravity. And we find G as 0.7 divided by 0.44. And that would give us 1.6 according to the written answer here. And then for double I, we are told that in a laboratory on the moon, the plastic cube is held stationary using a clamp in a beaker of oil of density 850. The lower face of the cube is 3 centimeters below the surface of the oil. Use your answer to CI to calculate the pressure due to the oil on the lower surface of the cube. So again, here we have pressure due to liquid, and the formula is rho GH. We have the rho given here. This is the density. And we have the gravity from part I. So this would be our G. And finally, we want the height. Remember that the height is only from the point at which we're calculating to the top. So this is 3 centimeters. Of course, we have to convert it to meters. So to go from centimeters to meters, you have to divide by 100. So 3 divided by 100 gives us 0.03, and we plug it here as the height. So now that we have rho and G and H, we simply multiply them together to get the pressure, which is 41 Pascal. Figure 1.1 shows a cylinder made from copper of density 9,000. The upper face is at a depth of 2.7 below the surface of the liquid. The pressure due to the liquid at the upper face is 560. Calculate the density of the liquid. So again, this is another instance of P equals rho GH. G, of course, is 10. The pressure is 560. We want to find the density, so let's write X here. And the height, of course, is 2.7 divided by 100. So we can write it as 0.027. And then, using simple mathematics, we can find X by transferring everything to the other side. So X will equal 560 divided 10 times 0.027. And if we calculate that, we find it equal to 2,100 kilograms per meter cubed. Explain why the cylinder does not float in this liquid. Of course, if it does not float, this just means that it is denser than the liquid. And this does make sense because we are given that the density is 9,000. The density of the cylinder is 9,000, and the density of the liquid was calculated as 2,100. So of course, the cylinder is denser than the liquid, so it will not float inside. Figure 3 shows an oil tank that has a rectangular base of dimensions 2.4 by 1.5. The tank is filled with oil of density 850 kilograms per meter cube to a depth of 1.5 meters. Calculate the pressure exerted by the oil on the base of the tank. So of course here we are given dimensions of the base. So in order to find the pressure, we can either use rho GH or F over A. So we have two rules for pressure. P equals rho GH and P equals F over A. Sometimes questions will require you to use both rules at the same time. This is one of these questions here. We are given the depth. So H is equal to 1.5. Of course, G is 10. And we are even given the density. So we have rho here as 850. So we are given everything we need to calculate the pressure. So we need to use the first rule for question I. So pressure equals rho GH, which is 850 times 10 times 1.5. Let's check the answer for this. This will give us 12,750, which is approximately 13,000 Pascal. Now, in question double I, we are required to find the force, so we have to use the second rule now. Given the pressure, which we already have, which is 12,750, we can calculate the area as 1.5 times 2.4. And now we have an equation in F. 12,750 equals F over 1.5 times 2.4. We can take these to the left, the other side. We have F equals 12,750 times 1.5 times 2.4. So therefore, the answer to that will be 45,900, which is approximately 46,000 newtons. In question B, we are told the force calculated is the weight of the oil. Calculate the mass of the oil. Of course, this is just W equals mg. So we can use either this number or this number, doesn't really matter. So 45,900, or I'll just use 46,000. This is equal to mass times 10. So therefore, we divide by 10, and the mass is 4,600. And don't forget the unit of kilograms. Figure shows a hollow metal cylinder containing air floating in the sea. The cylinder has length 1.8. It floats with 1.2 submerged in the sea. The bottom of the cylinder has an area of cross-section 0.8 meters squared. The density is 1,020. Calculate the force exerted on the bottom of the cylinder due to the depth of the sea water. Of course, as long as we're given density and height, we know that we're going to need to calculate pressure, even if they did not explicitly ask for pressure, but we're probably going to need to calculate it anyway, since pressure is force over area. So again, after getting the pressure, we can get the force from the second rule. So let's see the workout here. First, we're going to calculate the pressure using rho GH, and we're given everything we need. We're given the density, which is 1020. And you need to figure out, again, which height you're going to use. Are you going to use the 1.2 or the 1.8? So we want the pressure at the bottom. We want the pressure here. So we calculate the distance from the point at which we're measuring the pressure to the top of the liquid, not to the top of the cylinder, of course. So this is our correct height. So therefore, we use rho GH 1020 times 10 times 1.2. And this is the pressure. Now, since pressure equals force over area, taking the area to the other side, we can say that force equals pressure times area. So therefore, the pressure that we have, 12,240, is multiplied by the area of the base, which is given as 0.8 in the problem itself. There it is. And you multiply both by each other, and you get 9,800 newtons. Next, we are told deduce the weight of the cylinder and explain your answer. Now, since the cylinder is floating, so it's in equilibrium, so therefore the force that we calculated in B, which is the force by the liquid on the cylinder, must be the same as the weight of the cylinder. Otherwise, the cylinder will move. It will move up or down. So now that we know that it's floating at a certain level, we know that it's in equilibrium, so the net force must be 0, and the weight must equal the upward force exerted by the water, which is like the upthrust of the water. A scientist fills a container with seawater. The container has dimensions 30 by 30 by 40. The density is 1020. Question B says, figure 2.1 shows a submarine. It is fully submerged in the sea. The atmospheric pressure is 100,000 and the total pressure on the top surface is 500,000. Calculate the depth of the calculate the depth of the top surface of the submarine below the surface of the sea. So we want to calculate the depth, and we are given pressure. So we'll probably be using P equals rho GH. This is the pressure of the liquid. But we should also know that the total pressure would be rho GH plus P atmosphere. So since the total pressure here is 500,000 and the atmospheric pressure is 100,000, we can figure out that the pressure due to the liquid, which is this part here, is equal to 400,000. So you simply subtract the atmospheric pressure from the total. And then you can use rho GH in order to find H. So since rho is 1020 and G is 10, and we don't know H, so we can just write an equation like this and use it to find H. So H is going to be 400,000 divided by 1020 times 10, which is what we did here in the written answer. And we got 39 meters for H. In double I, we are told a hatch on top surface has an area of 0.62. Calculate the downward force. Of course, we can simply use F over A equals P. We can take the A to the other side. We can say F equals P times A, pressure times area. We already have the pressure, and the area is 0.62. Of course, we want the total pressure because they said due to the total pressure. So we're going to use the 500,000, and we're going to multiply it by the 0.62. And we get an answer of 310,000 newtons. Figure 1.1 is the top view of a rectangular padding pool of constant depth. The pool is filled with seawater. The volume is 264. Calculate the depth of the pool. Now, in order to find the depth of the pool, first we need to find the area of the base. So the area of the base here is simply, or base area equals 44 times 20. And that gives us 880 meters squared. Now you should know from geometry that the volume is equal to base area multiplied by height or depth, of course. Now we know that the volume here is 264. So this is equal to 880 multiplied by the height. So the height equals 264 divided 880. Let's check the answer here. So 264 divided 880 on the calculator gives us 0.3 meters, which is the value we got for the depth. In B, we are told the mass is 2.7 times 10 to the power of 5. Calculate the density of the sea water. Now that we have the volume, so since we have the volume and we are given the mass, we can use the equation for density, which is rho equals m over v, mass over volume. And we simply plug in the two values we're given, as is done here. And we calculate the density as 1020. In C, we are required to calculate the pressure due to the seawater at the bottom of the pool. So now that we have the density, we can use the value that we obtained for rho. We can write P equals rho GH. Since we have the depth of the pool already, which is 0.3, and we calculated the density, which is 1020, and gravity is equal to 10. So you multiply these three by each other, and you find the answer here, which is 3,100 Pascal. Of course, this is here a typo. I apologize for that. There should not be this 0.3 here. It's just 3,100 Pascal. State a suitable instrument for measuring the dimensions given in figure 1.1. So you cannot say ruler, of course, because you cannot measure 44 meters with a ruler. So how can you measure a long distance? You use what we call a tape measure. And by long distance, I mean from 1 to 100 meters, for example. So anything within that range is measured using a tape measure. A large stone block is to be part of a harbor wall. The block is supported beneath the surface of the sea by a cable from a crane. Figure 2.1 shows the block with its top face a distance h beneath the surface of the sea. The force acting downwards on the top face of the block due to the atmosphere and the depth h of water is 3.5 times 10 to the power of 4. The top face has an area of 0.25. Calculate the pressure. So again, this is repeated. We use P equals F over A. We are given F, we are given A. So we can simply plug them in and calculate the pressure for part I. For part I, the atmospheric pressure is 1 times 10 to the power of 5. Calculate the pressure due to the depth of the water. So the pressure, the total pressure here is 1.4 times 10 to the power of 5. So this is here the total pressure. This is equal to 140000. This is P total. This is equal to P liquid plus P atmosphere. And P liquid is what we don't know. And P atmosphere is 100,000. So P liquid must be 140,000 minus 100,000, which is 40,000. So you simply subtract the two quantities from each other, and you get 4 times 10 to the power 4 Pascal. Now that we have the pressure due to the liquid, we are asked to find the depth, h. So we're going to use P equals rho gh again, given our answer for P, and given the density that they gave us, and gravity is 10, of course, we can take these two values and put them in the denominator. So we get 4 times 10 to the power 4 divided by 10 multiplied by 1020. And this is what I did actually here. And the answer is 3.92, or just 3.9 to two significant figures. In B, we are asked to suggest two reasons why the tension force is not 3.5 times 10 to the power of 4. So the force acting downwards on the top face of the block is 3.5 times 10 to the power of 4. And we are asked to figure out why this is not equal to the tension. It would be equal to the tension if the block is in equilibrium and these are the only two forces acting. So we have tension up and we have force, let's call it force due to liquid or whatever. And we are being asked to figure out why these two are not equal, because other forces have not been factored, such as what? Such as the weight of the container itself, the weight of the block. So W, this has not been factored. Furthermore, there is an upthrust of water here. So other than the downwards force that they told us about, we also have an upthrust force by the water. These are two forces that have not been factored, and these would change the result. So this is why they are not equal to each other. The block is lowered so that it rests on the seabed. State what happens to the tension force in the cable. Of course, if the block is resting on ground, then there is no tension in the cable. And the tension becomes 0. An archaeologist is investigating a shipwreck and discovers a wooden box on the seabed. The dimensions of the lid of the box are 1.2 by 0.8, and the pressure is 1 times 10 to the power of 5, the pressure of the atmosphere. The lid is 15 meters below the surface of the sea. The density is 1020. Calculate the pressure due to the seawater. So the pressure due to the seawater is simply PL, pressure of the liquid, which is rho GH. So let's check the answer here. Yes, the pressure on the lid due to the water is simply rho GH, which is 1020 times 10 times the depth. And we are told that the lid is 15 meters below the surface. So therefore, the depth here will be 15. And we multiply these together and we get the pressure. And then you have to differentiate, of course, between the pressure due to the liquid and the total pressure. And the equation is P total equals P liquid plus P atmosphere. So all you have to do here to get P total is just add the value that you got, which is we like to approximate to two significant figures. So 153,000 becomes just 150,000. And then you take that and you add it to the atmospheric pressure, and you get 250,000 Pascal. Next, we want to find the force. Of course, the force would be pressure times area, because pressure equals force over area. We are allowed to take the area to the left. It will multiply the pressure. So we take the pressure that we got, which is 250,000, because they said total pressure. And we multiply by the dimensions of the box, 1.2 and 0.8, as given in the problem. And we find the total force. Of course, this is also another mistake. This is supposed to be newtons, not Pascal. In question B, the force needed to open the lid is not equal to the value calculated in III, which is the 240,000 newtons. Suggest two reasons for this. Again, it's the same as the last question. We have to factor the weight of the lid as well as the upthrust on the lid. But you have to talk about the lid, not the box. So you have to say the lid. That's why it's between quotation marks. We have to talk about the weight of the lid and the upthrust on the lid, because the wooden box itself is resting on solid ground, so it doesn't necessarily have the same forces as the lid. The final question in this video says figure 2.1 represents the cross-section of an oil tanker in a river. The bottom of the tanker is 15 meters below the surface of the water. The area of the bottom of the tanker is 6,000 meters squared and the density is 1,000. Calculate the pressure at the depth of 15. So this is repeated. Depth would be height, and we would use rho gh. So 1,000 for density. It's given in the problem, in case you don't know where we're getting the data from. This is the density, this is the height. We multiply rho by g by h, and we get the answer. Calculate the force. So again, we use F equals PA. You can start to see the pattern. Most of the questions usually require these two rules when we're talking about pressure. And it's pretty much the same idea again. You multiply the pressure that you got here by the area. So the area is already given also in the problem here. The area is given as 6,000 meters squared. So therefore, the force is 9 times 10 to the power of 8. This is the force due to the water pressure on the bottom of the tanker. So this is the force that is pushing up like this. Now, since the tank is in equilibrium, the weight of the tank has to equal this force. So therefore, the weight of the tank must also equal 9 times 10 to the power of 8. And I would like to point your attention to the verbs that were used. Here we have calculate. Here we have deduce. So deduce means that you're not going to do any further calculations. It's something logical that you have to figure out. In question B, we're told the tanker sails out onto a calm sea. The density of the seawater is greater than the density of the river water. So we're moving from the river to the sea, and we want to state and explain any change in the depth of the bottom of the tanker below the surface. So let's analyze this mathematically. The density of seawater is greater, and we know that pressure equals rho g h. So if density increases, then pressure must increase. So the force that is pushing the tanker up must increase. So therefore, the tank will rise because the density is greater and the pressure is therefore greater. This brings us to the end of our video. I hope this has been beneficial. Thank you for watching.